Hi Year 12 and welcome to this video on organic chemistry. Organic chemistry is the chemistry of carbon, that wonderful sixth element on the periodic table. It used to be thought of as the chemistry of molecules produced by living organisms. However, now it's known as the chemistry of carbon, after some organic molecules were produced from inorganic materials. Now, before we get too far ahead of ourselves, let's take a look at some of the key types of formula we're going to come across in organic chemistry. So, some of the types of formula here. We've got the empirical formula. The empirical formula simply gives me the ratio of elements. So it tells me that for every 2 carbons, I will have 5 hydrogens. So 2 carbons to 5 hydrogens. The molecular formula will tell me the actual type and number of atoms present in the molecule. So it tells me that this particular molecule here has exactly 4 carbons and 10 hydrogens. The structural formula here shows me exactly how the atoms are connected to each other. So it gives me the type of atoms, I've got carbons and hydrogens, and the number of them, 4 carbons, 10 hydrogens, and also how they're connected. All the carbons in a row, all the hydrogens around the outside. The condensed structural formula is the same as the structural formula, but what it does is it takes everything that is connected to a carbon and puts it just beside the carbon. So these two here are the exact same molecule. On the first carbon, there are 3 hydrogens, 1, 2, 3. On the second carbon, there are 2 hydrogens, second carbon, 2 hydrogens. On the third carbon, there are 2 hydrogens, third carbon, 2 hydrogens. And on the fourth carbon, there are 3 hydrogens. Fourth carbon, 3 hydrogens. So it's nice and condensed and a bit easier to communicate. Even more condensed is the skeletal formula. The skeletal formula only shows me the carbons. So every angle or every corner is a carbon. So 1, 2, 3, 4 carbons. And the lines that we see are the bonds that connect the carbons. So between our 4 carbons, we have 1, 2, 3 bonds, therefore we have 1, 2, 3 lines, where each end is a carbon, each corner is a carbon. Each of these 4 formula actually represent the same molecule. They all are the same thing. So they give me differing levels of detail. This one only tells me there's 2 carbons to 5 hydrogens, not very useful. This tells me the exact number of carbons and hydrogens, there's actually 4 to 10. This one tells me how they're connected, very useful, and these two are simply condensed versions of our most detailed. We also have to keep in mind the number of bonds that each element can form. Hydrogen only ever forms 1 bond. Oxygen forms 2, nitrogen forms 3, carbon always forms 4. That's really important to keep in mind when drawing and naming organic molecules. Now halogens, that's group 17 elements on the periodic table, also only form 1 bond. So we can call this the honk rule, H-O-N-C, which is 1, 2, 3, 4 for the number of bonds they can form. All organic molecules are the same in that they've got a carbon chain, so some sort of chain of carbons with lots of things hanging off them. Those things that hang off them are called functional groups. And the functional groups influence the chemical and physical properties of the molecule. These are the functional groups we're going to see throughout this year. The first ones we'll look at are these 3. The alkanes, which just have carbons to carbons and carbons to hydrogens, so they don't really have a functional group per se. We'll also look at alkenes, which have a carbon to carbon double bond somewhere in the molecule, and alkynes, which have a carbon to carbon triple bond somewhere in the molecule. After that, we'll look at alcohols, which have an OH somewhere on the carbon chain. We'll look at haloalkanes. Haloalkanes are an alkane with a halogen. A halogen is a group 17 element. The ones that we'll see are chlorine and bromine. So some sort of chlorine or bromine somewhere on the molecule makes it a haloalkane. We'll also look at amines, which will have an NH2 somewhere on the molecule. And we'll look at carboxylic acids, which have the C double bonded to an O and an OH coming off the same carbon somewhere in the molecule. So those are the various functional groups that we'll see throughout the year. As I said, the first group that we'll look at is the hydrocarbons. Hydrocarbons contain only hydrogen and carbon. Hydrocarbons, hydrogen, carbons. The three types are alkanes, alkenes, and alkynes. We say that alkanes are saturated. That means they've got the maximum number of H's they could possibly get on that molecule. Every carbon has 4 bonds, and all the bonds that aren't going to other carbons are going to hydrogens. Alkenes and alkynes, we say, are unsaturated. Because they've got double bonds and triple bonds, there is still space to add more atoms to the molecule, and we could have more hydrogens on there. So we say that they are unsaturated. We'll now take a look at the physical properties of hydrocarbons. The first physical property we need to know about is how the melting point and boiling point changes with the size of the carbon chain. This graph here shows that as we get more carbons going left to right across the horizontal axis, as we go left to right, our boiling point and our melting point increases. Here's our temperature scale on the vertical axis, and we can see that as we go across, we get more carbons, our boiling point increases. So that's the first trend we need to know. One way I like to think of this is, it's much harder to shake 5 bowling balls than it is to shake 5 marbles. Because they are bigger particles, they take more energy to shake them, more energy to break the bonds between the particles. That's why the melting and boiling point increases as the molecules get bigger. We also need to look at solubility. So how do our hydrocarbons dissolve? Well, they can dissolve in other non-polar solvents really well. So for example, petrol and oil would be miscible or soluble in each other. However, they are insoluble in polar solvents. So if we had oil and water, they would form 2 distinct layers. The water is polar, the oil is non-polar. They are not going to dissolve in each other. I'll show you an example of that later in the video. First up, alkanes. Alkanes have the general formula CnH2n plus 2. That means whatever the number of carbons is, to figure out the number of hydrogens, you can double it and then add 2. So for example, if there were 2 carbons, you would have 2 times 2 is 4 hydrogens, plus 2 makes 6 hydrogens. So the formula for that alkane would be C2H6. The functional group, as we said before, in alkanes, is only carbon to carbon and carbon to hydrogen bonds. That's all we're going to see. And we need to remember, as per the Honk rule, that carbon forms 4 bonds and hydrogen only forms 1 bond. All alkanes have the ending ane in their name. So every single alkane will have the end of its name ending in ane. Then there are a wide range of prefixes available, and the prefixes, or the first bit of the name, tells us how many carbons are in the longest carbon chain. So here are the possible prefixes that we could come across. If there's only 1 carbon in the chain, it's meth. 2 carbons is eth, 3 carbons prop, 4 carbons bute, 5 carbons pent, 6 carbons hex, 7 carbons hept, 8 carbons oct. So if we have an example here, we've got 1, 2, 3 carbons in our longest carbon chain. So 3 carbons means the prefix, or the start of the word, is going to be prop. Because it's an alkane, only having carbon to carbon single bonds and carbon to hydrogen bonds throughout the whole molecule, it must end in ane. So this molecule will be propane, propane. Let's look at some more complex examples. For the first one, our carbon chain only has 1 carbon, therefore we are going to use the prefix meth. Because it's an alkane, the suffix will always be ane, therefore this molecule is methane. Example number 2, our longest carbon chain is 1, 2, 3, 4. Therefore our prefix will be bute. because it's an alkane, only having carbon-to-carbon single bonds and carbon-to-hydrogen bonds, it's going to have the suffix -ane. So that's butane. On to our longest example. The suffix again is always going to be -ane because it's an alkane with only carbon-to-carbon single bonds and carbon-to-hydrogen bonds. Now we need to figure out what the prefix will be. 1, 2, 3, 4, 5, 6, 7, 8. 8 is oct, so this is going to be octane. Now, alkanes can be more complex than just those straight chain simple ones we named just then. We can also get branched alkanes. Branched alkanes are when you have a side chain, which is called an alkyl group. So some sort of carbon chain coming off to the side. For that we use YL instead of -ane to help us name the side chain. So for example, a 1-carbon side chain would be a methyl side chain. A 2-carbon side chain would be ethyl. A 3-carbon side chain would be propyl. We also have to note the position of the side chain with a number. And we always start numbering at the end that is closest to the side chain. Let's have a look at some examples. Example number 1. Well, we've got a 4-carbon chain as our longest carbon chain, regardless of where you start. Even if you start up here, it's a 1, 2, 3, 4 carbon chain as our longest chain. So that means to name the longest chain with 4 carbons, we have a bute. Because it's an alkane, having all carbon-to-carbon single bonds and carbon-to-hydrogen bonds, it must end in -ane. So the core of our molecules are butane. As you can see here, let's assume we started, we called this our main chain. We've got this side chain here coming off. So we need to name that. It's a 1-carbon side chain, so we're going to call it methyl. So we have a methyl butane. And we also need to give the position of that side chain. So as I said just previously, we always start counting on our parent chain at the end closest to the side chain. That's this end here, if this is our side chain. So this will become carbon number 1, 2, 3, and 4. And our methyl group is on carbon number 2. For number 2, let's identify the longest carbon chain. So we can either say that this 1, 2, 3, 4, 5 chain here is our longest, or we can say that this 1, 2, 3, 4, 5 is our longest, or this way. It doesn't really matter. So let's pick 1, 2, 3, 4, 5. Let's say that's our longest carbon chain. Being 5 carbons long, it's going to have the name pent. Because it's an alkane, all carbon-to-carbon single bonds and carbon-to-hydrogen bonds, it's going to have the ending -ane. So that's a pentane. We now need to name this side chain. It's a 2-carbon side chain, therefore it's going to be called ethyl. And our 2-carbon side chain is on carbon number 3. So it's going to be 3-ethyl pentane. We always separate numbers and word with a dash. On to the third example. Let's identify our longest carbon chain. 1, 2, 3, 4. Or 1, 2, 3, 4, 5. That's our longest carbon chain. So I'll start numbering here. 1, 2, 3, 4, 5. We always start numbering at the end closest to a side chain. Well, this is going to be our side chain, and it's in the middle carbon. So it doesn't actually matter which end we start numbering at. You could start here if you like. Either way, our longest carbon chain is 5 carbons long, so we have a pent. We're all carbon-to-carbon single bonds and carbon-to-hydrogen bonds, so it's an -ane, alkane. And we have a 1-carbon side chain, which is a methyl, and that is on carbon number 3, 3-methyl pentane. So that's how to number and name branched alkanes, where there are side chains. Now, if there are multiple side chains, what do? Well, all the names will go at the start. They're all going to be a prefix. So just like we had methyl pentane, all of our side chain bits are going to go at the start of the name. If there's more than one of the same side chain, so for example we had 2 methyl groups, then we can use di if there's 2 of them, or tri if there's 3 of them. And we must give numbers for all of their positions. So let's have a look at some more examples. I've left the hydrogens off just to make this a little bit more simple to look at. So here our longest carbon chain is 1, 2, 3, 4. Doesn't matter where you go, 1, 2, 3, 4, it's always going to be a 4 carbon long chain. So I'm going to start numbering there and call that my longest carbon chain. Because it's 4 long, it's a bute. These are all alkanes, so it's a butane. Now I've got 2 methyl group side chains. So I need to have methyl there, and because I've got 2 methyl groups, I need to say, actually, I'm a dimethyl. Whereabouts are they? Well, one is on carbon number 2, and one is on carbon number 3. So 2, 3, dimethyl butane. The reason I need to give these numbers is because both methyl groups could be on the same carbon. It could be 2, 2 dimethyl butane, which, in fact, let's have a look here. Longest carbon chain, 1, 2, 3, 4. Again, you could start numbering here or here, doesn't matter. 4 carbons is bute, it's an alkane, so it's butane. And we've got here 2 methyl groups, 1, 2. This is not a 2 carbon side chain, this is 2 1 carbon side chains, because this 1 carbon comes off this 1 carbon comes off this one. So again, we've got dimethyl, and this time both methyl groups are on carbon number 2, so it's 2, 2 dimethyl butane. So you can see how those 2 molecules are similar and also how they're different. To our third example, longest carbon chain, 1, 2, 3, 4, 5. 5 carbon means pentane. We have 1, 2, 3 side chains. They are all 1 carbon long. So they're all methyl. And this time, because there's 3 of them, we say that they are trimethyl. And what numbers are they on? 1 is on 2, 1 is on 3, 1 is on 4. So 2, 3, 4, trimethyl pentane would be the name for this molecule. Again, all the hydrogens should be around the molecules to make every carbon have 4 bonds, but I've kept them off just to keep this picture a little simpler. Alkanes can also exist in ring structures called cyclic alkanes. So these structures are given the prefix cyclo, and we can see that here all the carbons are connected in a ring. Because there are 1, 2, 3, 4, 5, 6 carbons in our ring, this is a hex. All carbon to carbon single bonds and carbon to hydrogen bonds, so it's an alkane ending in ane, it's a hexane. But because it's in a ring, we need to give it this prefix, cyclo. So this is cyclohexane. All cyclic alkanes have the general formula CnH2n. Our original alkanes had the +2 there. Our cyclic ones don't have that. We lose 2 hydrogens by connecting up the 2 N carbons and closing that ring. So we're going to look now at something called isomerism. First of all, we'll look at structural isomers, which can also be called constitutional isomers. Structural isomers have the same molecular formula, which means they have the same type and number of atoms, but they're connected differently. Here's an example of 2 structural isomers. Both of these molecules are C4H10. They both have 4 carbons and 10 hydrogens. But you can see they're connected differently. This one's in a straight line. This one has one of the carbons coming off as a side chain. So these are structural isomers of each other. And one way we can spot them is if they have the same molecular formula, C4H10, which both of these do, but they have different names. This is butane, being a 4-carbon chain. This is methyl propane, having a side chain coming off a 3-carbon chain. So your turn now. Can you please draw the structural isomers for C5H12? Keeping in mind that every carbon must have 4 bonds, every hydrogen must have only 1 bond. Pause the video here while you carry out this task. The C5H12 structures that I drew were these ones. A 5-carbon chain, all the hydrogens around, a 4-carbon chain with a 1-carbon side chain as a second structural isomer, and a third option is a 3-carbon chain with 2 1-carbon side chains coming off. Those are the 3 possible structural isomers of C5H12. Have another go. Draw the structural isomers of C6H14. Pause the video here while you carry out this task. The possible structural isomers of C6H14 are all 6 carbons in a row, a 5-carbon chain with a 1-carbon side chain on the second carbon, a 5-carbon chain with a 1-carbon side chain on the third carbon, a 4-carbon chain with 2 1-carbon side chains, one on the second carbon, one on the third, or a 4-carbon chain with 2 methyl groups coming off, both on the second carbon. I say this is the second carbon because we always start counting from the end closest to the side chains. That's this end, so 1, 2, 3, 4. It doesn't matter which end you start counting at here because they are both directly adjacent to the end of the molecule. Let's have a look at the chemical properties of alkanes. So one thing that alkanes can do is they burn. They undergo combustion. There's 2 types of combustion they can undergo. Complete combustion, where there's lots of oxygen gas and a blue flame, or incomplete combustion, where there is insufficient oxygen gas and we get a yellow sooty flame. The equation for complete combustion would look like this, where we have our alkane, C4H10, that's butane or methyl propane. We have 6.5 O2, forming 4 carbon dioxides and 5 waters. This is complete combustion because only CO2 and H2O are produced. If it's incomplete combustion, then as well as CO2, we'll also get some carbon monoxide, CO, or we could just get some carbon, C. So this is a complete combustion reaction because we only get these 2. Here you can see a typical laboratory Bunsen burner. Bunsen burners are fueled by LPG, which is a mixture of propane and butane. This is incomplete combustion. You can see it's yellow and sooty flame because the air hole is closed, limiting the amount of oxygen. As we open the air hole, it allows more air and oxygen to mix with the gas. Therefore we get clean or complete combustion where only CO2 and water are formed. You can see the flame becomes blue. That's one of the chemical reactions that alkanes can undergo. Another is substitution. Substitution is when one atom is replaced by another. So just like on a netball team or a rugby team, when you make a substitution, one player will go off, another player will come on. The same applies to our alkanes. These substitution reactions are slow. They take a lot of time. And they also need a UV light catalyst to help get the reaction going. The reagents, or the things that the alkanes will react with, will be chlorine, Cl2, typically dissolved in water, or bromine, Br2, also dissolved in water. This is a very pale green yellowy colour. This is a brown colour. And Br2 is the one you'll most typically come across in this type of reaction. Here I have some of that bromine water in a test tube. As I add a small amount of an alkane, hexane, you'll see that it forms a separate layer just on the top of the Br2. That's because the bromine is dissolved in water, which is polar, and our hexane is non-polar. Therefore, they will not dissolve in each other. As I take that test tube and give it a good shake, you'll see that the bromine has moved into our non-polar hexane layer, but no reaction has occurred. The bromine has simply moved from down below in the water to up above in our non-polar layer. As said before, this reaction is incredibly slow and requires a UV catalyst to make it occur. I'll now take this outside and put it in sunlight, and we'll look at it again after it's finished reacting. Coming back in from outside, you can see that it's started decolorizing. It's not yet finished. We'll take it outside to let it finish. There we are, all done, but I had to stand outside for about 5 minutes while this slow reaction took place. The balanced chemical equation looks like this, where we have a Br going on to the carbon chain and a hydrogen coming off. So one on, one off. You can see the Br replaces one of the hydrogens on the chain, and the H that came off joins with the other Br to form HBr, which is an acidic particle. So that's a substitution reaction, where a bromine, or a Cl if it was Cl2, goes on to the alkane and replaces a hydrogen which jumps off. So that's alkanes. I hope you found this video useful. Next up we'll look at alkenes and alkynes.